So just briefly touching back on statistical significance, it is important to make sure that you have a really clear understanding of the four different terms we're using. The test statistic is the actual value derived from a statistical test. It's the number we're calculating. It is the score of t. It is the calculated r. It is the calculated f. It's the value that we actually get from our data set and our sample. That test statistic is compared to a critical value. The critical value is the criteria for stating whether or not that test statistic has a p-value of less than 0.05. And the critical value is what we're getting from those tables. We're taking a look to find out what the degrees of freedom are. We're looking across the 0.05 to find what is the value that we need to exceed to be able to claim statistical significance. And in this case, it is equal or exceed. Did we get that value or better? If so, we have a significance of 0.05 or better. The p-value is the actual statistical significance value of a particular test. So again, if we're using tables and we find that we actually hit not only the critical value for 0.05, but we go along the table and find that our value actually exceeded that needed for 0.01 or 0.001, we could report a p-value of either less than 0.05, less than 0.01, or less than 0.001. If we're using a statistical package that actually calculates the exact p-value, then again, that's what we're reporting. For example, a p of 0.042. That would be the actual p-value. Now again, I generally suggest that we round to 2 decimal points unless we're reporting a p-value of less than 0.001. The alpha level, again, is the criteria for accepting test statistic as significant, and that, again, is set pretty much standardly at 0.05. So p-value is the actual calculated chance that you're wrong. Alpha, 0.05, is the least amount of willingness we are to accept being wrong. Test statistic is what we actually calculate. Critical value is the value that that test statistic needs to equal or exceed for us to be able to claim statistical significance. So if we have a statistically significant correlation, our next step is, again, effect size, judging the meaningfulness of the size of that correlation. And what we do is we calculate the proportion of shared variance between the two variables, and that is the coefficient of determination, often simply referred to as r squared. And how we calculate r squared? We square r. So this is probably one of the simplest ways to do an effect size that we're going to run across. So for example, our study and test scores correlated non-significantly at 0.88. But assuming we had a few more participants in that study, we could calculate the effect size. And at that point, we would simply square 0.88 by itself. So we'd basically multiply it, 0.88 times 0.88. In this case, we'd find that r squared is 0.77. Now, r squared does equate to a percentage. So note that though r ranges from 1.0 to negative 1.0, and an r of 1.0 is 100% correlation, an r of negative 1.0 is 100% correlation, and an r of 0 is 0% correlation. However, any other r is actually not on a proportional scale. In other words, r is not exactly a measure of percentage of shared variance, except at the very extremes, no correlation or absolute correlation. Everywhere else, it actually tends to be a slight overestimation of the actual relationship. And that's why we need to actually calculate r squared. So though r was 0.88, that didn't mean that it explained 88% of variance. It actually explains about 77% of variance. And once we have r squared, that's often what we'll use for Venn diagrams showing the relationship between two variables in a correlation. So in this case, we find that studying is fairly highly related and explains about 77% of test scores, according to this data set. But that also means that there's a percentage of test scores that is unrelated to studying. It might be cognitive ability, it might be past experiences with the classes, it might be whether or not you were able to get the textbook, whether you read the textbook. It also depends on how we define studying. And also, some of studying is not related to test score. In other words, there's some wasted effort there. Things you studied that weren't on the test, for example. So again, this gives us a way to visually represent how much of variance is being explained from one variable on the other. So again, this is referred to as a Venn diagram, and it's a fairly easy way to visually tell people what's going on when we find a relationship between variables. Now we can also use the Venn dieselgram. I'm sorry, I just had to, but we'll move on from that very quickly. So again, 77% is the portion of shared variance, but that also, by its very nature, indicates the proportion of unshared variance, which is 1 minus r squared. In other words, how much is not explained? 23% of test score in this particular sample was explained by something other than studying. In other words, we don't know what accounted for it, but it wasn't studying. So, judging the meaningfulness of the correlation, again, a general guideline rules of thumb. And this, again, varies depending on your field. And I would say that this is actually a pretty extreme view of effect size. So you'll often find this or something very similar to this, referring to no to weak relationships, moderate relationships, and strong relationships as far as r squared. So an R of 0.0 to 0.29, which is an R squared of explaining 0 to 8% of the variance, is usually no to a weak relationship at best. An R of 0.3 to 0.69 is considered a moderate relationship. That's explaining 9 to 48% of the variance, R squared. And finally, to say that we have a strong relationship is 0.70 or higher, which is explaining 49 to 100% of the variance in R squared. Now, I would note that this is across all fields of science. Honestly, in psychology, and specifically applied psychology, if we could explain 8 to 15% of human behavior with a particular predictor, that's actually pretty good. Human behavior is very complex, has a lot of predictors. So also, though this is kind of the standard across sciences, I would also be a little cautious at calling an 8% relationship weak to none if it's significant, especially if that 8% is really meaningful with an organization. Let's say you're only explaining 8% of variance, but by using that 8% of variance, you increase the likelihood of a successful hire in a multinational company by 8%. That means 8% of the people being hired are successful when before you use this technique, 0% were. So basically, you're only explaining 8% of the variance. There's only an 8% increase in the success of your hiring process because of this correlation that you start using. But that's 8% of people that wouldn't have done well in the past that are doing well now. Now, if you're hiring, let's say 100 people, that's 8 people that don't need to be fired now that may have needed to be fired in the past. Each one of them has training to become a successful employee that costs $50,000. Per year, with just 100 employees, that 8% may mean you're saving the company $400,000. So just recognize that there is the rules of thumb, there's the statistical guidelines to effect size, but you also want to be a good practitioner. You want to ask, how meaningful is an 8% increase in the success of reading, or an 8% increase in the success of a particular intervention, or an 8% increase in successful hires or successful training, where that 8% is allowing you to make better decisions, a small increase, but still an increase. And what is the ripple effects depending on the size of the organization? So how would you report all this? Something like this. First, again, you're going to say what you did. A Pearson product moment correlation coefficient was calculated, and you're now going to say on what? Determine the relationship between study time and test score. You're now going to report what you found. There was a non-significant positive relationship between hours spent studying and test score. We're going to report the R, an italicized R. We're going to report the degrees of freedom in parentheses, a 3. We're going to report what we actually calculated, 0.88, and then we're going to report the P, in this case, greater than 0.05. Now, if we were reporting this particular finding, that's where we would stop because we did not find significance. But if you had found significance, you would then follow it up with R squared, also italicized, and the value, and then because you found an effect, you'd put it into English. The more hours spent studying, the higher the person's test score. So now let's go to the Spearman correlation. So Spearman created an alternate equation to allow correlations with ordinal data. So this is a non-parametric statistic used to measure ordinal data or nonlinear relationships. So if you violated the assumptions of the correlation, which include it has to be a linear relationship and it has to be continuous, interval or ratio data, then you may be able to run a Spearman correlation. It measures the consistency in the ranks, not linear relationships. It converts scores into ranks and then looks for the relationship between those variables. For the smallest x, is it also the smallest y? Now, the actual equation that Spearman came up with is shown here. And we're not going to use that equation because honestly, it's a little complex and there's an easier way to do it with the tools that we already have. And that is to convert the data. So the first thing to recognize is that if you actually have two variables that are already ordinal, they're already rank ordered, there's no conversion necessary. You can just use the following tables and equations that we're going to walk through with that data. But a lot of the times we may be using a Spearman correlation because we have a violation of nonlinear relationship or some other violation in the actual nature of the interval, or I'm sorry, the ratio data that we have or the interval data that we have. So let's, for example, say that you check for skewness and kurtosis and both of your continuous variables have violated those assumptions. They're both skewed or they both have extreme scores, and you are uncomfortable doing a mathematical alteration such as taking it to a logarithmic score, or you don't want to lose those outliers. What you would do is convert the scores to ranks and then run it through a Spearman correlation, because the Spearman correlation does not have assumptions of normality of data. You do not need to worry about skewness or outliers or kurtosis in a Spearman correlation because it isn't made to look at continuous data. It's made to look at ordinal data. So we can convert the continuous scores into ordinal scores and then run those ordinal scores through a Spearman correlation. Now that might seem a little confusing, but what I'm telling you is that there are really two reasons we would use the Spearman correlation. The first one is we have ordinal data. It is not continuous, it's ordinal, and therefore this is the appropriate statistic. The second one is that we have violated the assumptions of normality of data, or one of our variables is ordinal and the other one isn't. So we're going to convert any of the continuous variables into ordinal data so that we can run a statistical analysis. So let's look at the formula we're going to use. So the first thing that we need to do is we need to convert the scores if that's what we're doing. So for example, let's say I have, I'm wanting to correlate exam 1 versus exam 2. Continuous data, it basically ranges from a score of 0 to 100, and I have the person's scores on exam 1 and exam 2, and I have 5 participants. What I'm going to do is basically change their scores to rank order. So looking at exam 1, I'm going to basically find what was the highest score, what was the second highest score, what was the third highest score, etc. And in this case, I'm going to go ahead and make the lowest score a 1. The next highest score a 2, the next highest score a 3, the next highest score a 4, and 5. So 5, the highest number, represents the highest score. And I'm going to do that also for exam 2. So again, at the end, I've converted the continuous data into ordinal data. Now again, if I already have ordinal data, I would not have to do this step. What happens if the rank score, what if ranks are tied? So for example, I've got now in exam 2, I've got two 90s. So clearly my lowest score is a 69, my next highest score is a 74, that's the 2. My highest score is the 92, that's a 5. What do I do with the two 90s? Basically what you do is you take the two ranks that they're tied on and you add them together and divide by 2. So in this case, it would be ranked scores of 3 and 4. I would add 3 plus 4, which is 7. I would divide by 2, and both of them get a 3.5. And the next slide will just walk through that simple math. So again, I take the number of tied ranks, I sum them, and I divide by the number of tied ranks. So in this case, my tied ranks there was a tie between rank 3 and 4. If there was a tie between 3, 4, and 5, I would add 3 plus 4 plus 5 and divide by 3. And that would give me the value I'd put on all of the tied scores. So once I've converted these into rank order, I'm going to have the same process I had with the correlation. Again, we have our hypothesis, no relationship versus a relationship. I'm going to determine the critical region, and again, from our degrees of freedom, I'm going to calculate what I actually need to find. Now notice that when we look at the critical value for Spearman's R, the degrees of freedom start at 5. And at 5, I need a perfect correlation to claim significance. And in fact, at 6, I need about the score that I needed for a 3 degrees of freedom on the correlation. So again, if we remember the correlation coefficient chart, at about 16, we were needing about a 0.40. Here we need about a 0.50. So again, recognize the Spearman correlation is a more robust test as far as rejecting the alternate hypothesis. In other words, it is not a very powerful test. It takes a stronger effect for it to claim significance. And this is an adjustment for the fact that it no longer has assumptions of normality of data. So once we have those ranked scores, we're going to do the exact same thing we did with correlation. We're going to compute the sum of products, we're going to compute the sums of squares x, and we're going to compute the sums of square of y, and you're going to see the same table we used before. The only difference here is that their scores of x and y, we're not using their original scores, we're using their ordinal scores. But we're doing the exact same thing. We're going to add up their ordinal scores, and we're going to get the means. And again, in this case, if we look at x, 2 plus 1 plus 4 plus 5 plus 3 is 15. And we're going to see the same on y because both of them are no longer on the original scale, they're just ranked ordered. 15 divided by 5 is 3, so that's our mean. So we're basically going to now take each person's ranked ordered score and minus the mean. We're going to get those values, we're going to run through the table, and again, we're getting our sum of squares, our sums of squares for x and y, and our sum of products. Our sum of products in this case is 8.5, our sum of square x is 10, our sums of square y is 9.5, and we're going to put them in the exact same equation that we use for correlation. So again, we're going to plug them in, we're going to run the numbers, and we're going to get a correlation of 0.872. The degrees of freedom is still n minus 2. In this case, we still have 5. Minus 2 is 3. And again, basically, we're right off the chart. The critical value here would be perfect correlation. We don't have it, therefore not a statistically significant relationship. There is not a significant statistical relationship between study time and exam score based on the Spearman correlation. And again, we can take a look at that critical value table and see where we're at. And again, for this to have been significant, if we calculated a 0.872, if that number hadn't changed, we would have needed a degrees of freedom of at least 7, which means we would have needed 9 participants. So again, you can see that for basically the exact same data, we would need more participants to find significance. If that score didn't change when we calculated it with more participants, then we would have needed to get to significance for the correlation, the Pearson product moment correlation coefficient, which only required one more participant.